大家好，我是清华大学电机系黄眼介。Today I'm going to give you the second lecture on transmission line. Last time we already introduced some concept, and today we're going to look into the transmission line in a little bit more details. And first, I'm going to talk about standing wave again, but this time there will be a lot of calculations and also the analysis. And then we need to figure out the impedance at different location on the line, because impedance is the total ratio of the voltage to current, and that is an important value that we need to understand. And then I'm going to show you two quite unique transmission line with the length of half and quarter wavelength. And finally, I want to give you a solution of the whole transmission line by adding a generator circuit to the line. And again, finally, I'm going to give you a little bit of review. So the first part of my lecture is about a standing wave. And on this slide, I want to refresh your memory that the transmission line circuit consists of a generator, a transmission line, and a load. And of course, the generator is going to generate the power and signal propagating down this transmission line, and finally deliver the signal to a load for some application. But don't forget that usually, in addition to having a forward propagating signal, we'll have some reflection of the signal from the load, forming a standing wave on the transmission line. And last time, we already calculated the general solution for the voltage and current. And in these two expressions, I assume that there's no loss, so that we can simplify the analysis a little bit. And you can see that in this voltage or this current, they both contain two terms, one propagating in the forward direction and the other propagating in the backward direction. And we could continue to reorganize those terms by taking out the first term and group the rest into the two terms in this parenthesis. And you can see that there's a phase associated with the second term. That is a function of position. So basically, this term is going to oscillate in different locations. And the one at the beginning basically just tells you the propagation of the signal. And you can do the same thing to organizing the current and come up with this expression. And a long time ago in the electromagnetic one, I talked about a complex number. And I told you that a complex number can be always calculated into a polar form with a length and also a phase angle like this. So we're going to use this to continue to do the calculation for this voltage signal. So now you can just take an absolute value of this voltage signal and put it in front of this polar form complex number, and then you generate a phase that is a function of position. And turn out that if you want to recover the real signal, then you multiply this phasor expression with exponential j omega t, so that you can recover this harmonic signal. So once you do this operation to this phasor expression, then you come up with an envelope function in front of a cosine signal. And inside this cosine signal, it tells you that the signal will oscillate with a frequency omega. And then there's a phase that is a function of position. And we all know about this cosine function because it's just a sinusoidal signal oscillating with time, but there's an envelope function associated with it. So if I simply plot this signal along distance, then I end up having an envelope function shown with the red dash curve like this. So within this red dashed envelope, there will be a signal oscillating back and forth, up and down. For example, you see inside this red dash curve, there's a green curve and blue curve. They are plotted at different time points. For example, the green curve was plotted with omega t2 equal to pi, and the blue curve was plotted at different time. And for this particular figure, I use gamma equal to 0.5. That means that 50% of the voltage signal is reflected. And you can see that the envelope function has a periodicity of half wavelength. And so you can recognize that this envelope function basically is the standing wave envelope. Because I only have 50% reflection, so this is now 100% contrast standing wave. So you can see that the minimum point of this envelope does not drop to 0. If I plot this signal at another 2 time points, then I end up having this curve. And again, the envelope function does not change over time, because here the envelope function is just a function of position. But within this envelope function, you have cosine omega t plus phi z, so it's going to change over time. So for these 2 curves, the green curve and blue curve, that happen at different time, omega t1 equal to pi over 2, and this omega t2 equal to 3 pi over 2. So basically, now we understand that from this analysis, I can really construct the signal on the transmission line over time and over distance. And in general, there's a forward propagating wave and also the backward propagating wave forming an envelope versus distance. And the voltage and current simply oscillate between this envelope. And the voltage envelope and the current envelope in general are different. So let's look at this again, the signal for the voltage. And the ray curve again is the envelope function. And what oscillating inside are these 2 curves, the green curve and blue curve. And at different time location, the curve is going to move up and down, but all the signal is going to be confined within this ray dash curves. And so if I also plot the current signal at the same time, then I end up having this pattern. And you can see that basically the envelope function does not change, but the actual amplitude of the current and voltage are different. For example, if I look at this point, and this point, it corresponds to a voltage sigma. You can see that the voltage signal basically swing to the maximum value within this big envelope. We call this anti-node. But at the same time, this current is reaching the minimum point. So it's interesting to see that when the voltage signal reaches the maximum point, the current will also hit the minimum point. And I can also show you that at different time, when the voltage is oscillating at these 2 time point, it reached minimum point here. So you can see that the green and also the blue curve hit the minimum point of the envelope function. We call this a null for the standing wave pattern. But for this same time, if I look into the current signal, then the current signal in fact swing to the maximum point inside this envelope. So we reach a conclusion that when the voltage hit the maximum point, the current will reach the minimum point. And from the patterns on the right hand side, you can also see this conclusion. Now, let's approach this from some mathematical calculations. So let's go back to the original expression for the voltage in the forward direction and backward direction. and also the current in the forward and backward direction. Well, basically the amplitude, the envelope function is determined from the value and also the phase. So on the last page, we already have a conclusion that when the voltage reaches the maximum point, the current will reach the minimum point. So on this plot, the red dash curve is associated with the voltage on the transmission line, and the black dash curve is associated with the current on the transmission line. And so you can see that when the red curve reaches the maximum point, the black dash curve always oscillates at the lowest point. And the separation of the two peaks or the two minima is by a distance of half wavelength. So mathematically, we can see this from this expression. So if you set this phase to be integer multiple of 2 pi, then this expression is going to give you 1 plus gamma inside this parenthesis, which will give you the maximum value of the voltage for the envelope function. The reason for this, the minus sign here, is because we count the distance from right to left and set z equal to minus L along this direction. And the 0 point is at the low of the transmission line. And because this is the, in general, negative value, so we set this to be a negative value for the phase. And then if we also look into, again, this expression and this expression, and set this phase right here to be R multiple of pi, then you're going to be calculating the minimum point of the voltage and also the maximum point of the current. So again, you see this very similar expressions, except that the sign before this, the gamma is changed from plus sign to the minus sign for the voltage, but the negative sign before this gamma for the current is going to change to the maximum it's going to change to the positive sign, so that you get the maximum value of the current. So after this point, you might be wondering why the maximum voltage point will correspond to the minimum current point. And my interpretation is that the total power on this line is going to be the multiplication of the current and voltage. And on average, the power on this line is a constant value. So whenever your voltage reaches your maximum, then your current has to drop to a minimum, so that if you average over all time on this line, the total power propagating on this line can be conserved. Now, we need to have a way to describe how good a standing wave is, because on a transmission line, the reflection from the lobe could be 100%, could be 50%, could be some percentage. And the reflection of the signal from the lobe is going to tell you how efficient you deliver the energy to the your application. So we define a value called the standing wave ratio, which is the maximum voltage over the minimum voltage for the envelope function, or equivalently is the maximum current over the minimum current for the envelope function. And turn out that the standing wave ratio is given by this expression. For example, if we have 100% reflection, so gamma, the value is equal to 1 or minus 1, then you end up having S equal to infinite. So it tells you that on the line, there will be a perfect standing wave with 100% contrast. So at the null, you're going to have 0 value. This is the perfect standing wave. And now I can give you the 2 examples for the perfect standing wave and with the standing wave ratio equal to infinite. So that's the recall this formula for the reflection coefficient for the voltage. And this reflection coefficient, if you spell it out with the low resistance or low impedance and characteristic impedance, then in general it's a complex number with some magnitude and also some reflection phase. Suppose that if you just open this circuit, take out this low, so you have an open circuit associated with this transmission line, so your low impedance is going to be infinite. With this ZL equal to infinite, basically this Z0, the characteristic impedance, will be negligible. So you take out this and then you cancel these two, and then you get gamma equal to +1. So this means that for this case, the reflection phase here is 0 or 2 pi. With this calculation, it gives you 100% reflection, and the voltage, the reflection voltage signal at this open circuit is going to have the same phase as the instant voltage. Okay. And another case where you have infinite standing wave ratio is that you close down this circuit and have it to be a short circuit right here. So if ZL equal to 0, then you put it into this expression, get a reflection coefficient equal to -1, and don't forget that this reflection coefficient is defined for the voltage. So this means that the reflective voltage signal is going to be out of phase with respect to the instant voltage. That's why you get a 180-degree phase difference here. And because the reflected signal is out of phase with the respect to the instant signal, so you end up having no voltage here because they just simply cancel each other. And for this case, you get reflection coefficient equal to -1, and then your standing wave ratio can be infinite. This means that you're going to have a perfect standing wave or 100% contrast standing wave on this line. Now, what if the low impedance is not 0 or infinite, is some value? Then we look into this situation on this page. Well, suppose that we are working with the lossless line. So in general, you don't want to work with the line with a very large loss. So in general, it's a good approximation that we talk about a lossless transmission line where you don't have the resistance, you don't have a conductance, and your characteristic impedance is simply a real number. That is the square root of L over C. And with this, you can write your reflection coefficient to be like this, where RL is the resistive load at the end of the transmission line, and R0 is the characteristic impedance. And apparently the reflection phase is related to the value of RL and R0. For example, suppose that your load resistance is larger than your characteristic impedance. And so this value is larger than this value, so gamma is a positive number. So if you have a gamma being a positive number, then your reflection phase is going to be equal to 0 or integer multiple of 2 pi. So this means that the reflected voltage is going to be in phase with the instant voltage. And so right at the boundary, the two signals are added up together to a big value. So it turned out that right at your low resistance, you have the maximum voltage here. And again, I want to remind you that this red dash curve is associated with the voltage, and the black dash curve is associated with the current. So whenever you have a maximum value for your voltage, then you have a minimum value for your current. And so we can also conclude that whenever you have this forward voltage in phase with the backward voltage, then your forward current and backward current will be all phase that give you the minimum value at the boundary. And the other case is that if the low resistance is less than your characteristic impedance, and this gamma will turn out to be a negative value. So negative value will give you the refraction phase equal to 180 degree, or R multiple of pi for the refraction phase. So the voltages on this boundary is going to be added up destructively, so you will end up having a minimum value for your voltage at the boundary. But we just say that whenever you have a minimum value for your voltage, then you will have a maximum value for your current. So for this case, with the low resistance less than your characteristic impedance, right at this point, your standing wave pattern is going to start from this line and in this direction. Okay. Now, I want to give you a little bit review on what I have told you in this session. Well, number one, I want to tell you that the signal reflection from a low forms a standing wave in the transmission line. And I want to emphasize this several times throughout this lecture, because this is quite fundamental for this topic. And now everybody knows that the standing wave pattern has a periodicity of half wavelength. And this half wavelength turned out to be also the period of the transmission line properties. And on the standing wave pattern, the location of the maximum voltage will coincide with the minima of the current. And on the other hand, the location of the minima voltage are going to match to the locations of the maximum current. And we also define a figure called standing wave ratio to tell you how the standing wave pattern look like a perfect standing wave on the transmission line. For example, if the standing wave ratio is infinite, then this means that you're going to have 100% reflection of the signal from your low. So this is pretty much I want to tell you in section 1. Thank you.